I want to start off Unit 4 by kind of setting the stage for what's going to happen in this unit. In Unit 3, we spent a lot of time and effort getting good at determining whether a series would converge or diverge. So what we're going to do in Unit 4 is use a lot of those tools we learned about series convergence and divergence. And in particular, we're going to come up with series that help us approximate functions. So in this section, we're going to be learning about what's called Taylor polynomials, and then eventually Taylor series. And then all those tools we learned in Unit 3 to help us determine if a series converges or diverges are going to get applied here in Unit 4. So the first step of doing that is to come up with what's called a Taylor polynomial. Now, if I just threw the definition for a Taylor polynomial at you, it would seem like I pulled it out of thin air and it wouldn't make much sense why we would want to use it. So what I want to do instead is kind of give you a motivation for what a Taylor polynomial does, and then we'll see how it works. Okay, so let's just start by talking about a basic function, e to the x. Okay, we have calculators that can calculate this for any value of x we want to plug in. But let's say we either needed to do that by hand, or we wanted to program a calculator to calculate those values for us. Okay, that's easier said than done because I would already need to know the precise value for e, and then be able to do exponents of that. So instead of doing it that way, what we're going to do is we're going to come up with a Taylor polynomial approximation. Okay, so again, I've just thrown a phrase at you that doesn't have any meaning yet. Let me give you kind of a silly way of talking about this first. So we're going to start with a really, really bad approximation of e to the x. Okay, we're going to come up with a linear function that's vaguely like e to the x. Okay, so we're going to make these two requirements true. The function we come up with should have the same value at 0 as e to the x. And it should have the same derivative at 0 as e to the x. Alright, so let's see what we need to do to make that true. F of 0, that would be e to the 0. Well, anything to the 0 power is 1. F prime of 0. Alright, well hold on, I need to find the derivative. So f prime of x, well the derivative of e to the x is just e to the x. So I'm going to do e to the 0, once again that's 1. So if I was going to come up with a linear function to approximate e to the x, it wouldn't be a good approximation, but that linear function would be, let's see, a first derivative of 1. And if I plug in 0, I get 1. So that's going to be a slope of 1 and a y-intercept of 1. So I'm going to write that as g of x equals, instead of mx plus b, 1x plus 1. So there it is, my terrible approximation of e to the x. Okay, now obviously a linear function is not going to look much like my exponential function, right? If I get anywhere away from 0, these two graphs are going to be very different. Okay, so what I might want to do instead is, well, let's say I wanted to have a bigger degree function. Like maybe I could have a quadratic function. So let's look at that really quick. Okay, so once again, we're trying to approximate e to the x using a quadratic function, but this time I want 3 different things to be true. The value should agree at 0, the first derivative should agree at 0, and the second derivative should also agree at 0. So let's think for a minute about what a general quadratic function looks like. Okay, we should have something that looks like ax squared plus bx plus c. And just like last time, my goal is to make the value, the derivative, and this time the second derivative all agree with e to the x. Okay, so we've already found the value, derivative, and second derivative for f. Now let's find all that for this g of x that I'm coming up with, this quadratic function. So g of 0 would be c. Let's find g prime of x. So if I took the derivative of this, I would get 2ax plus b, which means g prime of 0 would be b. And then, if I want the second derivative of that function, it would be 2a. So g prime of 0 is just 2a. Okay, so I need to make sure that all these values are equal to the values I got for f. So g of 0 needs to be equal to 1. G prime of 0 needs to be equal to 1. And g double prime of 0, which is 2a, needs to be equal to 1. So I've got c equals 1, I've got b equals 1, and if I solve this guy, a equals 1/2. So I just found the quadratic function that's going to make all 3 of those requirements happen. Okay, so I've got a, b, and c. So my quadratic approximation is going to be 1/2 x squared plus 1x plus 1. So this should be a better approximation than my linear function was, if still maybe not perfect. So this is the basis of what a Taylor polynomial does. Okay, it's the idea that we could try to find a linear function, or maybe a degree 2 function, or maybe like a degree 17 function to approximate whatever function we're looking at. Now, if we had to go through this process every time of finding derivatives and checking that things are equal and finding the right values for a, b, and c, it would be extremely time consuming. Okay, so in general, we're not actually going to go through this process. I just want to show you where Taylor polynomials come from. Okay, so let me scroll down a little bit. I've kind of already done some work for us on this, and I don't want you to stress about where this comes from just yet. But in general, if I wanted a degree n polynomial to approximate e to the x, this is what I would get. Right? You could write that in sigma notation, or you could just write it as the sum of the terms from 1 through x to the n. Okay, so I would have a 1, an x, a 1/2 x squared, and then apparently a 1/3 factorial x cubed, a 1/4 factorial x to the 4th, and in general, the term that goes with x to the n is just 1/n factorial. Okay, so we're going to start seeing factorials show up a lot here. So something I want to look at really quick to help us understand what's going on here, I want to show you a visualization of these approximations we were doing. So what I've got set up here, in blue is e to the x, and in red is going to be our Taylor polynomial approximations. So let's start with our degree 1 approximation, that linear function we found. If I'm very close to x equals 0, yeah, those lines are very close. But if I get further away, it's kind of a terrible approximation. Alright, then we did a degree 2 approximation. Okay, anywhere near x equals 0, those lines are very close together. They eventually spread apart, but it looks like a pretty good approximation. I could keep working with this, maybe do a degree 3 approximation. That's even better. Or degree 4. Or degree 5. The higher degree I let my approximation go, the closer these lines are going to get to each other. Okay, so if I want a really, really good approximation, I just work out a few more terms. If I don't care as much about accuracy, maybe I don't do as many terms. Okay, so this is the idea of a Taylor polynomial, and now that we've kind of explored how we could do this very tediously and manually by hand, I want to give you a formula for how to find Taylor polynomials. So if we've got some function that we can take derivatives of, then here's our definition for a Taylor polynomial. Now, this is going to look complicated. You might be wondering, what on earth is this number c? Okay, so because last time I was plugging in 0 over and over again, c was just 0 in our example. Okay, just spotted a typo. This is supposed to be a c right here. Okay, so in general, the first term is just f of that value. We call that value c the center. So f of 0, then you do f prime of 0 times x minus 0. F double prime of 0 over 2 factorial times x minus 0 squared, etc., etc. Okay, so in general, if I wanted to take any function that has derivatives and try to approximate it using a Taylor polynomial around some value c, this is the formula that lets me do that. So I do want to emphasize at this point, this is something you have to have memorized. Okay, no way around it. We have to have this formula memorized because we're going to be using it over and over again in this unit. Okay, now, one thing we're going to start seeing more and more, it's kind of a pain to write like the 7th derivative of f. Instead, if you've got a superscript with parentheses, all that means is take the nth derivative. Okay, so we wouldn't write f with 7 prime symbols, we would just write 7th derivative of f. So it's just kind of a shorthand that makes life a little easier. Now, a special kind of Taylor polynomial, the one that we just finished looking at where the center is 0, that's called a Maclaurin polynomial. Okay, so you don't have to memorize this formula because it's just a special case of the Taylor polynomial formula where we let c equal 0. That's really the only difference. Okay, so at this point, I hope that you guys understand what the idea is of a Taylor polynomial. We're just taking some function and approximating it using a polynomial. Right? Some things like e to the x or maybe sine of x, you can't write those as polynomials, but we can get pretty close to those values using polynomials. These formulas just tell us exactly how to come up with those polynomials without having to go through the tedious manual process we did up here. Instead, we're just going to plug stuff into the formula until we get the degree polynomial we need and call it a day.